Hello everybody. Today we are diving into the world of tiny yet mighty world of nuclear physics. So buckle up because things are about to get weird and attractive. And by that I mean the strong nuclear force, not my jokes. First thing, let's talk about the strong nuclear force, also known as the force that keeps the nucleus of an atom falling apart like a weekend plants. Imagine the nucleus as a crowded party where the protons and neutrons are the guests. Now, protons are like those annoying guests who keep repelling each other because they are all positively charged. So, what stops this party from turning into a big chaos or a turmoil? Now enters the strong nuclear force. It's like the bouncer at the party, making sure everyone stays close without causing a scene. This force is a real heavyweight. It is about 137 times stronger than the electromagnetic force, which is one responsible for those protons trying to push each other away. But what is this strong nuclear force made of? All thanks to the particles called gluons. And yes, they do exactly what their name suggests. They glue. They glue the quarks together inside protons and neutrons. Okay, let's think of them as the ultimate superglue. Without gluons, the quarks would fly apart and so would the entire nucleus. Imagine trying to wrap a gift or a present with the tape that refuses to stick together. Definitely, it's not possible. So gluons are the particles which stick protons and neutrons together and makes the force heavy. Now, while the strong nuclear force is the hero holding the nucleus together, it has got a bit of short temper. It only works over very small distances, about 1 femtometer. For example, that is 1 millionth of a 1 billionth of a meter. So yeah, it's not going to see it in the action unless you have got a super microscope. Now, let's not forget about the weak nuclear force. It is strong force. If the strong force is the glue, the weak force is like a one friend who occasionally tries to change things up. It is responsible for processes like beta decay, where a neutron in the nuclear decides it's time for a makeover and transformation into a proton. This force is weaker than the strong force, so no surprise there, but it plays a crucial role in the production of energy in the sun. Also, the most important, half elements are formed in the universe. So weak force is weak, but it plays a very profound and crucial role in formation of elements in the universe and of course on the earth. So this was the basic piece of information that you must know while understanding the nuclear physics. So let's sum it up. The strong nuclear force is like the ultimate superglue for the nucleus, keeping those protons and neutrons tightly packed. Meanwhile, the weak nuclear force likes to mix things up, making sure the whole universe keeps evolving together. They make up everything sure that everything stays well in one piece. Radioactive decay is a concept of nuclear instability. An atomic nucleus is made up of protons and neutrons held together by strong nuclear force. However, when there is an imbalance between number of protons and neutrons, or when the nucleus is in an excited state with excess energy, it becomes unstable. To achieve this stability, the nucleus undergoes radioactive decay, emitting particles and energy in the process, which we call as radiation. There are several types of radioactive decay, each characterized by specific particles emitted and the changes occur in nucleus. Let's learn about the alpha decay. The mechanism of alpha decay. Alpha decay occurs when an unstable nucleus emits an alpha particle which consists of 2 protons and 2 neutrons, essentially helium-4 nucleus. This emission results in a decrease in both atomic number by 2 and mass number by 4 of the original nucleus, transforming it into a different element. Example, uranium-238 decays through alpha emission to thorium-234. Let's talk about the properties of alpha decay. The alpha particles are relatively large and carry a +2 charge because of their size and charge, they have low penetration power. This is important. And typically traveling only a few centimeters in air and being stopped by a sheet of paper or the outer layer of human skin. However, if alpha particle, if alpha emitting materials are ingested or inhaled, they can cause significant internal damage due to their high ionization potential. Here comes beta decay. Beta decay involves the transformation of a neutron into a proton or vice versa, accompanied by the emissions of beta particles, which are high energy, high speed electrons or positrons. Beta decay can occur in two forms. The first one, that is beta minus decay, and another one is beta plus decay. Let's talk about beta minus decay. The mechanism: in beta minus decay, a neutron is converted into a proton, an electron, and an antineutrino or antineutrino. The electron, that is beta particle, and the antineutrino or antineutrino are ejected from the nucleus. The atomic number of the nucleus increases by 1, but the mass number remains unchanged. For example, the carbon-14 decays into nitrogen-14 through beta minus decay. There are a few properties of beta minus decay. Beta minus particles are much lighter than alpha particles and can penetrate materials more deeply, requiring a few millimeters of aluminium or several centimeters of plastic to stop them. Beta radiation can cause damage to living tissues, particularly if the radioactive source is in close proximity. Now let's talk about the beta plus decay or positron emission mechanism. In beta plus decay, a proton is converted into a neutron, a positron, the antimatter or antimatter counterpart of the electron, and a neutrino. So a proton is converted into neutron, a positron, and neutrino. The positron is emitted from the nucleus, reducing the atomic number by 1 while leaving the mass number unchanged. For example, fluorine 18 undergoes positron emission to become oxygen 18, F18 to O18. Let's talk about the properties. Positron, once emitted, quickly interact with electron in their surroundings, leading to annihilation and production of gamma rays. Positron emission is particularly important in medical imaging techniques like positron emission topography, PET. Now let's talk about gamma decay. The mechanism: gamma decay occurs when a nucleus is in an excited state, which releases excess of energy in the form of gamma rays, which are high energy photons. This typically happens after the nucleus has undergone alpha decay or beta decay, but remains in an excited state. Gamma emission does not change the atomic number or the mass number of a nucleus, but it simply releases energy to allow the nucleus to transition to a lower state energy. For example, after cobalt-60 undergoes beta decay to nickel-60, the nickel-60 nucleus may emit or may not emit the gamma rays as it drops to a lower energy state. Properties: gamma rays have mass and no charge, making them highly penetrating. They can pass through several centimeters of lead or meters of concrete due to their high penetration power. Gamma radiation poses a significant health risk and requires substantial shielding to protect against this exposure of gamma decay. Here comes the neutron emission. Neutron emission is a type of radioactive decay where a neutron is ejected from an unstable nucleus. This process often occurs in nuclei that have an excess of neutrons and typically follows any other form of decay or fission. For example, certain isotopes produced in nuclear reactors, such as californium-252, can undergo the spontaneous fission, releasing neutrons in process. Let's talk about properties. Free neutrons are electrically neutral and can penetrate materials without being significantly deflected by electric or any kind of magnetic fields. However, when free neutrons are absorbed by any other nuclei, they can induce radioactivity or cause nuclear reactions, making neutron radiation a critical concern in nuclear reactors and weapons nowadays. Now let's talk about another part, that is decay series and chains. In many radioactive materials, a single decay event does not result in a stable nucleus. Instead, the product of one decay may still be radioactive, leading to a series of successive decays known as a decay chain. For example, the uranium-238 decay series is a well-known decay series chain. It begins with the uranium-238, which undergoes alpha decay to produce thorium-234. Then thorium-234 undergoes the beta decay to produce protactinium-234, and this process continues through a series of alpha and beta decays until it reaches the stable isotope, that is lead-206. Now, the importance. The decay chains are crucial for understanding the behavior of radioactive materials over time, as each isotope in the chain has its own half-life and radiation type. These decay chains are also important in radiometric dating techniques, where the ratios of parent to daughter isotopes are used to determine the age of rocks, minerals, and many other fossil parts. Now we'll talk about the applications of radioactive decay. The radioactive decay has a range of important applications across various fields. In medicine, it plays a crucial role in both imaging and treatment. For instance, in cancer therapy, radioisotopes such as iodine-131 and cobalt-60 are used to precisely target and destroy the cancerous cells, offering an effective means of treatment. Similarly, the positron emission tomography (PET) scans relies on isotopes like fluorine-18, which emit positrons. These positrons interact with electrons in body, producing gamma rays that are used to create detailed images, helping doctors to diagnose and monitor conditions like cancer and other neurological disorders. In archaeology and geology, radioactive decay is fundamental to dating ancient objects and geological formations. The radiocarbon dating, for example, uses the decay of carbon-14 to estimate the age of organic materials, providing valuable insights into historical timelines. Similarly, uranium-lead dating is employed to determine the age of rocks and even the Earth itself by measuring the ratio of uranium-238 to lead-206, helping to establish the geological history of a planet. The energy production also heavily relies on radioactive decay, particularly in nuclear power generations. The fission of isotopes such as uranium-235 within nuclear reactors releases a significant amount of energy, which is then harnessed to produce electricity. Additionally, the radioactive decay is used in nuclear batteries, specifically the radioisotopes, thermoelectric generators, RTGs, which then convert the heat from decay of isotopes like plutonium-238 into electricity. These RTGs, radioactive thermoelectric generators, are vital for space missions, providing a reliable power source for spacecrafts operating in environments of Sun and far from the Sun. In environmental science, radioactive decay is used in tracer studies to trace or track the movements of substances like pollutants or water to ecosystem. By analyzing the decay of specific radioisotopes, scientists can gain valuable information about the environmental processes and how they affect the world around us. Furthermore, understanding the radioactive decay is crucial in managing the nuclear waste, as it informs the design of storage solutions that must safely contain the radioactive materials for thousands to millions of years, ensuring the long-term environmental protections. So this was the basics and foundation understanding of the nuclear physics. You will have more such videos in this series called All About Nuclear Physics.